to Unit 7, Soils, Erosion, and Runoff. Selecting effective soil erosion and sedimentation control, or SESC measures, require a working understanding of how soil properties and site conditions affect the erosion, runoff, and sediment control processes. Please observe the site in this photo. As you can see, earth change activities can cause significant issues to nearby waterways, including the potential discharge of sediment-laden water to streams, rivers, and wetlands. Each earth change activity or site is unique. Therefore, several factors must be taken into consideration when selecting the SESC measures to manage soils and runoff on that site. Please remember from earlier in this course that Rule 1703 of Part 91 requires the landowner to provide a SESC plan for an earth change activity. This unit provides more information regarding soil types and their properties, how they interact with water, and how to determine what SESC measures are best suited for site-specific conditions. Soil texture is one of the major factors in determining erosion, runoff, and sediment control at sites undergoing an earth change. Soil texture refers to the size or combination of sizes of the soil particle and is the most important soil property. Having an understanding of different soil textures is important for the control of soil erosion and sedimentation. The three major size categories of soil, from smallest to largest, are clay, silt, and sand. Soils consisting of 100% clay, silt, or sand are rarely found in Michigan. Generally, soils consist of varying percentages of clay, silt, and sand, and are named as such: sandy loam, silty clay, clay loam, etc. These names are used to categorize soils based on the relative percentages of clay, silt, and sand, as we will see shortly in the NRCS textural triangle. In general, sand is larger in particle size and heavier, therefore it drops out of suspension easier and faster. Silts have the consistency of flour and will stay in suspension longer. Clays are the smallest of particle size and will generally stick together. The texture of a soil can be determined in the field by rubbing a sample between the thumb and fingers. There are three easily distinguishable extremes. Sand feels gritty, silt feels floury, and clay feels smooth. This slide illustrates a profile of the three major categories of soil: clay, silt, and sand, and the blue arrows indicate the level of infiltration of stormwater moving through each profile. Notice how water infiltrates the furthest through the sand soil type, as the particles are larger and have more pore space in between, allowing for greater infiltration at the top of the layer and throughout the profile. Clay soils allow the least amount of water to infiltrate, as the particles are very small and are bound tightly together with greater cohesiveness. As you can see, silt is in between those two extremes. As just stated, soils generally consist of varied percentages of clay, silt, and sand. To help determine the soil type at a site, we can use the Natural Resources Conservation Service, or NRCS, textural triangle. The NRCS textural triangle is a tool used to determine soil type based on physical texture. In this tool, soil textures are classified by the fractions of each soil type present in a soil sample. Classifications are typically named for the primary constituent particle size or a combination of the most abundant particle sizes, such as sandy clay or silty clay. A fourth term, loam, is used to describe a roughly equal concentration of sand, silt, and clay, and lends to the naming of even more classifications, such as clay loam or silt loam. The left side of the triangle is % clay, the right side is % silt, and the bottom is % sand. When you take a soil sample and are able to roughly determine the percentage of each soil, such as through sieve analysis, you may use this triangle to better classify that soil. Find the percentage on each side and follow the line, as shown on the slide as a red line to where they meet. As you can see in this example, there's 15% clay, 70% silt, and 15% sand. They all meet within the silt loam classification. Please note that in general, soils tend to become less erodible when moving left in the triangle and more erodible when moving right in the triangle. Information about the soils on a particular site can be obtained in several ways. The most common are from published soil surveys or from field inspections. Soil surveys are published on a county basis through cooperative effort by the NRCS, Michigan Department of Agriculture and Rural Development, and other federal, state, and local agencies. In addition to soil texture, information within each survey includes maps of the location of soil series within a county, a description of the soil physiochemical properties, and an evaluation of the soil's suitability to support and sustain a variety of uses and activities. There are a few different ways to determine soil texture. First, you can send a soil sample to a lab for a sieve analysis. The sieve analysis will provide the percent clay, silt, and sand, and then you can use the NRCS textural triangle to obtain the exact texture. A soil sample can also be observed through field analysis, as described on page 7-2 and in Appendix 7A of the training manual, determining soil texture in the field. Simply rub a soil sample between the thumb and fingers. As stated earlier, there are three easily distinguishable extremes. Sand feels gritty, silt feels flowery, and clay feels smooth. For best results in identification, perform the field test in Appendix 7A on both dry and moist samples. Another option is to review the NRCS soil survey. However, this may not be completely accurate for urbanized areas. The Web Soil Survey, also through the NRCS, has good information when you are working with individual property owners. Once the texture of a soil has been determined, an SCSE planner can make certain inferences about how that soil will affect the erosion, runoff, and sedimentation processes on the construction site. Erodibility is a measure of a soil's susceptibility to raindrop impact, runoff, and other erosive force. Soil texture is one of the major factors which determine the erodibility of a certain soil. Factors such as cohesion, structure, and compaction can also affect erodibility, even in soils with similar textures. The NRCS has assigned all soils in Michigan an erodibility status or K factor. Higher K factors indicate a higher erodibility. In general, silty soils tend to be highly erosive, clayey and loamy soils tend to have moderate erodibility, and sandy soils generally have low erodibility, although very fine sands can also be very erodible. The amount of any given soil that will erode through the forces of wind and water is dependent on many factors in addition to soil erodibility. Slope steepness, slope length, soil cover, soil management practices, and the intensity of wind, rainfall, or runoff also have an impact on the total amount of erosion from a site. Potential erosion from a site is important when prioritizing Part 91 site inspections. The NRCS revised Universal Soil Loss Equation, or RUSL, is one method of estimating soil loss. Remember that soil texture refers to the soil particle, sand, silt, or clay, or combination thereof. Soil cohesion is the soil's ability to stick together. Clay soils tend to be the most cohesive, therefore they are the least erodible. Soil structure describes the arrangement of soil and the pore spaces located between particles. It is determined by how individual soil particles clump, bind together, and aggregate, which result in pores or interstitial spaces in between where water can move through. Soil compaction describes the process where soil particles are pressed together, thereby reducing the pore spaces between them. Remember that there are modifiers such as silt loam and clay loam. A silt loam contains more silt than loam, and a clay loam contains more clay than loam. Therefore, a silt loam has a greater erodibility than a clay loam, as clay particles stick together better. We just discussed the factors that affect a soil's erodibility. Now we will discuss the factors that affect erosion, which is slightly different. Remember that erodibility is a measure of a soil's susceptibility to raindrop impact, runoff, and other erosive forces, whereas erosion is the actual wearing away of the land surface by wind, water, ice, or gravity. Erosion of the land surface occurs as a result of several factors, such as soil erodibility, slope steepness and length, soil cover, and rainfall rate and intensity. We will be reviewing each of these factors in greater detail in the slides to come to gain a better understanding of how they can help determine the rate of erosion. However, first we will take a look at the NRCS Russell equation and how it illustrates how individual factors can alter the rate of erosion. Please refer to Table 7-1 in your training manual and on this slide. This table provides outputs from the NRCS Russell equation for estimating sheet and rill erosion from a site. As you can see in the table, the Russell equation takes into account the following factors: soil texture, slope percent, slope length, land cover, and geographic location by county. The equation will determine soil loss in tons per acre per year, which results in cubic yards of soil loss. The first row of the table is considered the baseline. Subsequent rows below have factors that are changed from the baseline information, and those changes are shown in bolded print. Take note of how changes in individual factors can change the amount of soil loss that can be expected to occur. Let's take a look at the silt loam in the first row. At a 6% slope over a flow length of 300 feet, with no land cover in Clinton County, Russell calculates a soil loss of 54 cubic yards. In the next row down, a sandy loam with all the same factors records a soil loss of just 24 cubic yards. And in the third row down, a clay loam with all the same factors records a soil loss of 45 cubic yards. In this specific case, the silt loam will have the most soil loss. The clay loam will result in lesser soil loss because of the cohesiveness of clay particles. Now, if we look further down the table, we will see a change in the slope percentage. Notice how the change in slope greatly changes the amount of soil loss. Let's look down a little further to see the change in the slope length, which also greatly affects the amount of soil loss as well. A change in the land cover appears to have the greatest impact on soil loss. The placement of a soil erosion control measure, such as straw or mulch, or keeping heavy, dense vegetation in place, minimizes the loss of soil considerably. The use of Russell can help you see this impact to better plan soil erosion control measures to be installed at a construction site. Although preventing soil particles from eroding is always the most effective method, preventing all erosion from occurring during an earth change is generally not feasible. Therefore, sediment control measures are often necessary to prevent damage to waterways and adjacent properties. Once soil particles have been dislodged through the erosion process, they are transported and deposited as sediment. The properties of the soil particles that are eroded have a strong impact on when and where those particles will be deposited. The most critical of these properties is once again soil texture. Determining the soil texture is important in selecting effective sediment control measures for a site. The settlement rate of a soil particle and the effectiveness of the sediment control measure is directly tied to soil texture. As you can see in the chart, particle size determines how effective the control measure will be. Sand is the largest and heaviest particle, allowing it to settle out of the water column quicker and easier than any other soil texture. Therefore, sediment control measures work best on sand-sized particles. Because silts and clays are smaller in size and lighter, they tend to stay in suspension in the water column much longer and do not settle out very easy without the help of a polymer. Because of this, it is very important to not only know the types of soils on your construction site, but to place your primary focus on erosion control methods such as staging and phasing. Erosion control is typically more cost-effective than sediment control because once soils start to move, it is more difficult and time-consuming to remove them from runoff water. This photo depicts a large construction site during a light rain event. In approximately the middle of the photo, you can see that sand particles are settling out behind a straw bale barrier. Clay and silt-sized particles are passing over this straw bale barrier, then through a small sediment basin, through a brush barrier, through multiple rows of silt fence, to finally discharge into a river towards the top left of the photo. This particular site has generally silty clays with some sand, and as you can see, the sand had settled out first in front of the straw bale barrier. The lighter particles are left to hopefully settle out in the sediment basin. However, it does not appear to be of adequate size to provide enough time for settlement. Because of this, those light particles continue through the flow path, pass through a brush barrier, which is not an adequate sediment control measure, and continue to pass through several rows of silt fence. The stormwater discharging into the river is noticeably laden with sediment. Therefore, the controls on the site are not adequately managing sediment and are not protective of the river. Being that the site is primarily clay soils, silty clays, that tells us that once sediment is in the runoff water, it will be difficult to get out. Therefore, we should focus more attention on erosion control measures and how not to destabilize those areas with highly erodible soils. If it is decided to use a sediment basin, then effort should be made to design it to correct size and detention time. If area is limited, then baffles can be constructed within the basin to increase the flow length and time in detention. Another option is to introduce a polymer into the sediment basin that could enhance settlement of the silt and clay-sized particles. However, once again, it is most cost-effective to control erosion first than to respond to sediment that is already in motion. This photo is a close-up of the discharge of sediment-laden stormwater from the construction site discussed in the previous slide. Even though several measures were installed through the construction site, they were not necessarily the appropriate measures for the site. A discharge of sediment-laden stormwater to a surface water of the state is a violation of Part 91. This photo is a close-up of another discharge point from the same construction site. Stormwater on the site had to flow through several small sediment basins, silt fence, and a 20-acre wetland to end up at this location. This photo was taken 3 days after a small rain event. As you can see, silt and clay-sized particles are still in suspension and are being discharged into a surface water of the state, a wetland and a stream, still several days after the rain event. Physical sediment control devices such as sediment basins and silt fence are most effective on sandy soils, moderately effective on loam soils, and have a little effectiveness on silt and clay soils. Therefore, an SCSE plan for a site with a soil that has significant amounts of silt and clay should be heavily reliant on soil erosion control measures rather than sediment control. If heavy reliance on sediment control measures is unavoidable, chemical controls, such as polyacrylamides, will be necessary to ensure compliance with Part 91. Now that we have discussed soil texture and the factors that affect erosion, we must next consider runoff. Runoff refers to the water that runs off the land as a result of melting snow or rainfall. An accurate estimation of the location, volume, and rate of runoff on a construction site during the planned development phase is critical in determining the eventual effectiveness of planned SCSE measures. In general, disturbing natural vegetation and developing a site will increase the amount of runoff from the site, thus increasing the potential for erosion. There are 3 important considerations when planning for runoff from construction sites. 1, where and how the runoff will travel on that site. 2, how much water will run off in total. And 3, how much water will be moving at any one time. Please note that items 2 and 3 are necessary to design and size SCSE measures. The nature and direction by which the runoff flows is a major consideration for selecting effective SCSE measures. In general, there are 2 different types of runoff on construction sites: sheet flow and concentrated flow. Sheet flow is the movement of water over the land's surface at a relatively shallow and uniform depth. Although all runoff from construction sites start as sheet flow, even with slight variability along slopes, sheet flows begin to accumulate, forming concentrated flow. Concentrated flow can be created by natural topography or human activities, such as ditches, berms, and stormwater systems. Concentrated flows move at a greater velocity and depth than sheet flows, thus creating greater erosive force on the substrate soil. Also, the more common and inexpensive SCSE measures such as silt fence and loose mulch generally do not function properly in concentrated flows. It is critical to identify the direction of sheet flow and location of concentrated flows on construction sites. One important consideration is identifying these patterns before, during, and after construction as construction practices often change the direction of sheet flow and the location and number of concentrated flows. It is necessary to have an accurate understanding of site topography to understand runoff patterns. For smaller, less complicated sites, this may be accomplished with a site visit. For larger or more complex sites, an accurate topographic map may be required in addition to a site visit. This slide provides further clarification of sheet flows versus concentrated flows. Sheet flows occur over a large area in a shallow uniform depth and have the lowest erosive force or velocity. They are shown on a topographic map as regular contour lines, as we will discuss in the next slide. Sediment control measures, such as silt fence, are most effective for sheet flows. Concentrated flows carry a large volume of water through a small area, result in extensive rilling or gulling, and have the highest erosive force or velocity. They are shown on a topographic map as irregular contour lines that come to an upslope, point, or curve. Sediment control measures are difficult in these instances and may not provide for adequate sediment removal from runoff water. This is figure 7-2 on page 7-5 of the training manual and identifies sheet and concentrated flow paths on a topographic map. Please note that runoff flows perpendicular to contour lines on a topographic map. In general, areas with low slopes and relatively straight and parallel contours are more likely to maintain sheet flows. Contours that are irregular in shape tend to represent areas where concentrated flows might form. Contour lines that come to an upslope, point, or curve generally represent concentrated flows. Please note that if you are designing an SCSE plan, you are not only taking in consideration the runoff that falls on the construction site, but also any flow coming into your site from adjacent areas as well. As discussed in Unit 4, slope is expressed as a ratio, a percent, or in degrees. We are going to spend time learning how to calculate slope as a percent using figure 7-2 in your training manual. In order to calculate slope as a percent, we need the change in elevation over a specific distance, and then multiply that number by 100. We are using feet as the unit of measure in this instance. Please note that it's important that the elevation change and distance are in the same unit of measure. Please look at the bright green line on the topographic map. This green line is the area on the site that we want to obtain the percent slope. The first thing we need to determine is the change in elevation. We take the lowest elevation of the line, which is 105 feet, and subtract it from the highest elevation of the line, which is 115 feet. 115 feet minus 105 feet equals 10 feet. The next thing we need to determine is the distance of that line. In order to do this, we must first review the map scale, which is 1 inch equals 200 feet. Now, if you had a physical map, you would simply use a ruler to measure the bright green line. In this case, that line is 1.5 inches in length. And using the map scale, we can determine that 1.5 inches in length equates to a distance of 300 feet. We next divide the elevation change of 10 feet by the distance of 300 feet, which equals 0.033. Lastly, we multiply 0.033 by 100 to equal a slope of 3.33%. Again, here's the actual calculation that we just discussed. The rate that water infiltrates into the soil and moves through the soil affects the amount and rate of runoff leaving the site. The infiltration rate is the rate at which water enters the soil at the surface and is controlled by surface conditions. The transmission rate is the rate at which the water moves through the soil and is controlled by the soil layers. In general, when the rate of infiltration and transmission through a soil is higher, the volume of runoff is lower. It is important to note that Part 91 does not provide any authority to regulate the volume of runoff. However, the volume of runoff is just as important as the rate of discharge of runoff because this information is necessary to select the appropriate SCSE measures for a site. The volume and discharge rate of runoff is impacted by the following variables: soil type, land use, rainfall, drainage area, and slope. The NRCS has developed a table for each variable, along with equations to calculate volume and discharge rates, which will be introduced in the upcoming slides. The first variable that we will discuss is soil type. Soil scientists have assigned all soils to one of 4 hydrologic groups based on infiltration and transmission rates, as shown on this slide and in Appendix 7B in your manual. The 4 hydrologic soil groups based on infiltration and transmission rates are: Group A. These soils exhibit high infiltration and transmission rates and low runoff volume. They are chiefly deep, well-drained soils, sands, or gravel. These soils have a low runoff potential. Group B. When thoroughly wet but not saturated, these soils display moderate infiltration and transmission rates and runoff volume. They are moderately to well-drained soils, generally moderate in depth, moderately fine to moderately coarse in texture, including sandy loam, silt loam, and silt. Group C. These soils have slow infiltration and transmission rates and higher runoff volume when wet. They are distinguished by a layer that impedes downward movement of water and are moderately fine to finely textured. This group includes clay loam. And then Group D. These soils have the slowest infiltration and transmission rates and the highest runoff volume. They are chiefly clay soils with a high swelling potential or have a permanent high water table. Other characteristics may include a clay pan at or near the surface and shallow soils over nearly impervious material. These soils have the highest runoff potential. It is important to note that infiltration rates, transmission rates, and runoff volumes of all soils are affected by climatic conditions such as freezing. Regardless of its hydrologic soil group, all frozen soils exhibit a high runoff volume. Appendix 7B in your manual contains a list of all soil types in Michigan, along with their hydrologic soil group, A, B, C, or D, or a combination thereof. Again, the hydrologic soil group will be used to calculate runoff volume and peak discharge. The second variable that we will discuss is surface characteristics, which is also termed land use. The surface characteristics or land use of a site greatly influence the volume and rate of water running off the land. Typical site development may increase the runoff volume substantially. For example, runoff will range from less than 5 or 10% of the total rainfall on heavily vegetated areas like woodlands, to nearly 100% of the rainfall for impervious surfaces like pavement. It is important to review the current state of the land versus what it will be like during and after construction, and account for how the runoff volume and rate will change based on the change in land use. The NRCS developed this table of runoff curve numbers to categorize runoff for various land use and soil type combinations. Therefore, the runoff curve number is based on the hydrologic soil group and the land use. Each curve number developed provides an index to the potential runoff. The higher the curve number, the higher the runoff volume. When a site has several combinations of soils and/or land uses, an average runoff curve number must be computed for the site to represent the runoff volume. The third variable that we will discuss is rainfall. The amount of rainfall used in estimating the potential runoff volume and discharge rate from a site is dependent on the site location, which is separated into zones 1 through 10, rainfall duration, and frequency. Figure 7-4 provides the 24-hour Michigan rainfall values in inches for frequencies of 2, 5, 10, and 25-year events. A 5-year rainfall, for example, is a rainfall that is expected to occur on an average of once every 5 years, or has a 20% chance of occurring in any given year. Similarly, A 25-year rainfall is a rainfall that is expected to occur on an average of once every 25 years, or has a 4% chance of occurring in any given year. Now that we have discussed the variables that are used to determine the volume of runoff and peak discharge, let's take a closer look at the definition and calculation of each. The runoff volume refers to the total amount of water that runs off a site as the result of a precipitation event. Generally, as a site becomes more impervious, the runoff volume increases. The total runoff volume is calculated by multiplying what is termed the runoff depth by the site area. We will look at the runoff depth in the next slide. Peak discharge refers to the maximum rate at which the runoff passes a given location in terms of volume and time. It is measured in cubic feet per second, or CFS, and must be determined to properly size water control structures such as diversions and spillways. The discharge rate is greatly influenced by the slope of the land that the water passes over. Therefore, the steeper the slope, the higher the discharge rate. As stated in the last slide, we need to determine the runoff depth in order to calculate the total volume of runoff. The runoff depth is determined based on rainfall and the runoff curve number, which can both be obtained from tables that we discussed earlier. Therefore, to determine the depth of runoff leaving the site, please use Table 7-3, Expected Runoff Depth in Inches. This table converts inches of rainfall to inches of runoff based on the runoff curve number assigned for the site, which, as mentioned earlier, you can obtain in Table 7-2. As stated earlier, the discharge rate is greatly influenced by the slope of the land. The effective slope of the site is the slope of the longest water path or water channel. As we discussed earlier, it can be calculated by dividing the elevation difference of the site by the flow length. Flow length is the water travel distance along the water path from the site outlet point to the most distant high point on that site. Again, topographic maps and site plans are very useful in determining elevations and flow length. Runoff volume and peak discharge calculations must consider all the water entering and leaving the site, not just what falls directly on the site. Therefore, one must determine the entire land area, commonly called a watershed, which contributes water to a given discharge point as shown in Figure 7-5. In this scenario, the entire upstream area must be included in the runoff calculations for Site A. Runoff calculations for Site B, however, would only include the rain that falls directly on the site because there is no upstream contributing area. There is one more variable to take into consideration when determining the peak discharge from a site, and that is unit peak discharge. Unit peak discharge takes into account the slope percent and the length of that flow path, as can be seen in Table 7-4. The unit peak discharge is used in the calculation to obtain overall peak discharge, as we will see next as we complete the practice problems at the end of Unit 7. Please note that the values in Table 7-4 are a function of the time it takes for runoff to travel through the watershed. This travel time becomes shorter as the flow length decreases and the slope increases. The shortest travel time for which the runoff is computed is 6 minutes, corresponding to a flow of 1.46 CFS per acre per inch of runoff. For combinations of flow length and slope that produce a travel time shorter than 6 minutes, a constant flow of 1.46 CFS per acre per inch of runoff should be used. Please refer to Appendix 7C, Practice Problem A, Calculating Runoff from an Undisturbed Site. You may want to remove this page from your training manual, as you will need to refer back and forth to the tables we discussed earlier to fill in the blanks. This general format will be used on the exam, along with all necessary tables and figures to complete the calculations. Please note that for each part of the problem, the specific table or appendix is listed so that you know where to look for that information. Allow me to set up the situation. A factory and parking lot is proposed to be constructed on 5 acres near Lansing in Ingham County. Runoff from the surrounding area is diverted away from the site. Assume that all runoff originating on the site leaves at the southeast corner. The site conditions are that the soil is a Boyer loamy sand. The slope is 2% over a water flow length of 800 feet. The problem: please calculate the volume of runoff and peak discharge generated at the outlet of the site during a 5-year, 24-hour rainfall event for the present undisturbed condition, which is dense grass. The solution: the first thing we are going to look for is the 5-year rainfall for Ingham County, which can be found using figure 7-4 on page 7-10. Here is figure 7-4, climatic zones and corresponding rainfall values. The problem tells us that the site is located in Ingham County. As you can see, Ingham County is circled in red and is located in Zone 9. The problem wants us to calculate the volume of runoff and the peak discharge generated at the outlet of the site during a 5-year, 24-hour rainfall event. If you look at Zone 9 under the 5-year, 24-hour event, you will see that the rainfall frequency is 2.98 inches. Let's go back to our original problem and enter 2.98 inches of rainfall as shown in red font on this slide. Please note that we will be rounding this number up later in order to use the value in another table. The next question is to find the hydrologic soil group for Boyer loamy sand. Please refer to Appendix 7B, Hydrologic Soil Groups for Michigan Soils, to find the soil type for Boyer loamy sand. Here is Appendix 7B, Hydrologic Soil Groups for Michigan Soils. Again, the problem tells us that the site has Boyer loamy sand. As you can see, Boyer is circled in red and is hydrologic soil group B. Please note that some soil types in this table have 2 letters associated with them, such as D/A. The first letter indicates the soil group in its natural condition. The second letter is for drain soils or if they have soil tiles. For the purpose of the exam, you will not encounter a soil type that has dual letters. Let's go back to our original problem and enter B for the hydrologic soil group as shown in red font on this slide. The next question is to find the runoff curve number for the site. Remember that the runoff curve number takes into account both the hydrologic soil group and land use. Please refer to Table 7-2, Runoff Curve Numbers for Selected Site Conditions, to find the appropriate runoff curve number for this site. Here is Table 7-2, Runoff Curve Numbers for Selected Site Conditions. The problem tells us that the site is undisturbed with dense grass. As you can see, dense grass isn't an option in the table. However, there is open spaces, lawns, parks, and golf courses in differing conditions, fair with grass on 50 to 75% of the area, and good with grass on 75% of the area. In this scenario, we would choose this category and in good condition, given dense grass as the describer. We already know that the soil group is B, so following that over as shown in the red lines on the slide, we see the runoff curve number value as 61. Going back to our original problem, please enter 61 for the runoff curve number as shown in red font on this slide. The next question is to find the expected runoff from the site. Remember that the expected runoff from a site takes into account both the runoff curve number and inches of rainfall. Because we have already determined these 2 values, we can place them in the table as shown. Please refer to Table 7-3, expected runoff depth in inches to find this value. Here's Table 7-3, expected runoff depth in inches. This is when we will have to round up the rainfall value that we obtained earlier from 2.98 to 3.0 inches. As you can see, the rainfall is only in tenths of an inch on this table. Once rounding up the rainfall to 3.0 inches and knowing the runoff curve number 61, we can see the expected runoff depth to be 0.37 inches. Let's go back to our original problem and enter 0.37 inches for the expected runoff from the site. Now that we have found all this information, we can next calculate the volume of runoff, which is the runoff depth multiplied by the watershed area. It is important to pay close attention to the units, as we will have to change inches to feet and acres to square feet in order to determine volume in cubic feet. The conversion is on this page for your ease. Please enter 0.37 inches of runoff first. This must be divided by 12 inches per foot for the conversion to 0.03 feet of runoff. Next, enter the site size of 5 acres, which was stated in the problem situation. This must be multiplied by 43,560 square feet per acre for the conversion to 217,800 square feet as the size of the site. Lastly, we will multiply the 0.03 feet of runoff by the site size of 217,800 square feet to give us a runoff volume of 6,534 cubic feet. Now that we have the runoff volume, the next thing to calculate is the peak discharge. In order to calculate the peak discharge, however, we must first determine the unit peak discharge, which takes into account the percent slope and water flow length that we were given in the problem situation. We can enter these two values now, a slope of 2% over a flow length of 800 feet, as shown in the slide. Here is Table 7-4, unit peak discharge. If we follow the slope percent of 2 and the flow length of 800 feet, we will find that the unit peak discharge is 1.46 CFS per acre per inch of runoff depth. Let's go back one last time to our original problem and enter 1.46 CFS per acre per inch for the unit peak discharge. Now that we have this value, we can calculate the peak discharge. Peak discharge is listed as Q sub 2, and unit peak discharge is listed as Q sub 1. At this point, we have all the information necessary to enter into the equation. 1.46 CFS per acres per inch multiplied 5 acres multiplied by 0.37 inches of runoff provides us with a peak discharge from the site of 2.7 cubic feet per second. There are 2 more practice problems in Appendix 7C of the training manual that are similar to the problem we just completed. However, they will show how different the volume of runoff and peak discharge is between an undisturbed site, to a disturbed site during construction, to a site that has been fully developed. Practice problem B is the same as A, but after the site has been graded. Look at the difference in volume and discharge rates between an undisturbed site A and a disturbed site B. Removal of the dense grass vegetation has increased the volume of runoff water from 6,534 cubic feet to 30,492 cubic feet, and has increased the discharge from 2.7 CFS to 12.2 CFS. These changes have an absolute effect on the type of soil erosion and sedimentation control measures to install, and amplifies the importance of staging a construction project to minimize the volume and peak flows to better manage erosion and sediment transport. In summary, the proper design and implementation of virtually all erosion and sediment control measures is dependent on an understanding of the erodibility and settlement rate of the different soil types found on a construction site, as shown here again in Table 7-5. The ability to identify soils, in conjunction with knowledge of how soil properties influence erodibility, runoff potential, and sediment rate, will allow one to identify potential problem areas both on and off the site.